you make mistakes early, you're good.
Yeah, that's right. The tension gets turned up a little bit, doesn't it? All right. So you're going to be bitter about that and write down, I don't like that, don't play with me. Next time, we'll
Course survey, I'll remember this one.
That's right, yeah. The stupid quiz that was a terrible idea. Yeah, it's all right. I'll know who wrote that. Big old grain of salt set on that. Yeah. Yes. Okay.
Well, okay, so you get anything for winning, or are you penalized for losing, or is it just like a...
No, it's just, again, the activity itself is the win, going through and trying to do things quickly. Yeah,
Okay.
and then also talking it through with your peers, because that's, again, reinforcing, because you may not see a key word in that definition that they see, and they're like, no, this is why it's that, and so it really helps you overcome a lot of those little things, and that you focus on the important pieces that you might not have seen the first time, or maybe you see the important piece that your peers didn't see. So that's really very good, I think.
We're all winners when we learn.
That's right. It really sounds very, very much like that, I know, which kind of bothers me, but yeah, I'm not much of a everybody wins type person. I like trophies for first place, But. Okay, so we're going to go through the Boltzmann distribution today and really focus on what role temperature plays in equilibrium. Okay, and so we'll begin with the Thermodynamics Laws. Just the first one, the Zeroth Law. Did you know there was a Zeroth Law? Anybody? There's a few of the people who have had me before know there was a Zeroth Law. They came up with the first law, the second law, the third law of thermodynamics, and then they realized they never defined temperature. And so the Zeroth Law, they couldn't change the numbers because that would mess everybody up. I mean, worldwide, right? And there would be arguments over which was the real first law of thermodynamics. And so they just said, let's just pick 0. So if we ever discover anything new that's before temperature, we're going to have the -1 law, which is really going to be a mess. Is that, probably not. But let's go with the Zeroth Law. And there's many ways to state it, but this is one way. So when two systems are in thermal equilibrium, they must share a property. Pretty generic. And we've called that property temperature. So when two systems are in thermal equilibrium, they're at the same temperature. That's another way to state it. But this is the more generic way of stating it. Two systems, the systems could be, they could be atoms, they could be tables, they could be the atmosphere. It's just, again, it's generically stated. When two systems are in thermal equilibrium, they share a property, and we call that property temperature. So how does that figure into thermodynamics? We really figure it in using the Boltzmann distribution, because temperature is what governs thermal equilibrium. And you know that something's at thermal equilibrium by whether it matches a Boltzmann distribution or not. So if something, the probabilities of the various excited states match a Boltzmann probability, then that's a system that's in thermal equilibrium. If it doesn't match those probabilities, then it's not at thermal equilibrium. So our thermal equilibrium systems are defined by the Boltzmann distribution. So we'll work with that today. We'll do the simple cases of a 2 or 3 level system, and we'll talk about how to work with the Boltzmann distribution. Please interrupt if there are questions or if there's anything that you want to clarify. And this is pretty straightforward, this part. But if there's any nuance in there that you're like, what do you mean by that? Please ask those questions. So everybody clear with this one? Or let's now use temperature in determining what the probabilities are for a thermal equilibrium system. part of thermo is defining a system, and so you can, we'll calculate we'll show two systems in thermal equilibrium today. So let's start with just a simple, let's do a 3-level system, okay? And the probabilities in populating these different levels, so this is the probability so this is P sub I, that's the probability of being in state I. And that's an index, it could be like 0, 1, 2, 3, so if it's 1, what's the probability of being in that first excited state? Or if it's 2, what's the probability of being in that second excited state? Okay, so P sub I. Now anytime you're dealing with probabilities, you have the event you're interested in divided by all the possible events. Follow me? Now all the possible events, one of the assumptions, and I saw this I think in some of your vocabulary words entries, was this equiprobability. This is governed by there being equal probability of all the different events, okay, in the denominator. And so this, there shouldn't be any statistical favor for this level versus that level, or this state versus that state. Although we will see eventually a sort of a favoring of the ground state based upon the Boltzmann probabilities. But if you have degenerate levels that have the same energy, then they're equiprobable. Okay. So in the denominator, we have the sum of all of the possible states. So the sum over I, we have G of I, which is the degeneracy. And then this Boltzmann distribution, E to the minus energy over KT. The energy of state I is right there. Boltzmann's constant is K, and temperature. So that's where temperature comes in. It's inside this Boltzmann distribution. And this Boltzmann distribution is the sort of the probability of being in state I is this factor, so we'll call that the Boltzmann factor, Gi e to the minus EI over KT. So the Boltzmann factor for state I divided by the sum of all the Boltzmann factors for all the states. And if you want a really clear example, I mean, Jerome went and found this because he knew we were doing stat thermo first. And so in his discussion board problem, it's very clear and clean, cleaner than what I'm probably going to have on the board. So look at his problem. It's like 2 pages long. He goes through this in great detail. Probably should just put that on the screen and walk through it. But I think it's better to do it by hand so you follow mentally through and you'll get my commentary as we go through it. But that's a really good, clean presentation of the problems that we're going to do today. And so it's this piece in the bottom and this piece in the top. The top is the Boltzmann factor, so terms there, Boltzmann factor, for a given state I. And then the bottom is the sum of all the factors. This bottom piece here serves the purpose of normalization. So when you're doing probabilities, you want to have a normalized denominator. You want to have all possibilities in the denominator. And so you're looking at what's the probability of this particular situation divided by all the situations. So if you're familiar with a deck of cards, there's 52 cards in the deck. That's the normalization piece, 52, and there's one ace of spades. So the probability of pulling an ace of spades out is 1 over 52. Okay? There's 13 hearts. And so the probability of pulling a heart out is 13 over 52. So that 52 piece is the normalization. It's all the possibilities. Now, in a 2-level system, we're just going to have 2 pieces here. A 3-level system will have 3 pieces here. What if we have an infinite number of possibilities? Okay, this could be an infinite sum. But the difference between all those energy levels, if we're going to be summing over all those differences are probably going to be small if there's an infinite number of possibilities. And so that's probably going to turn to an integral. And then that integral is probably something we could solve. And so you might, in some really extreme cases, have an integral in the denominator that you could solve analytically and then have a denominator for an infinite number of energy levels. So this is a possibility that it could still solve the problem. It would just go from a discrete sum of a countable number of energy levels and a countable number of possibilities to an integral, which would get, again, that's an infinite number of possibilities, but it would have a certain amount, something that's solvable for the denominator. And then you still have the individual Boltzmann factor for the state of interest. And so this normalization piece tells us how we break the energy level probabilities into their different pieces. It's a partitioning, and so we call it the partition function. I don't know any other way to describe the partition. I mean, like in this room, we have 3 partitions, and we've divided the group into, the back row, the middle row, and the front row. And the front row has nobody in it, okay? But we've partitioned the room into different pieces, and the same kind of thing happens here with this partition function. It's the total possibilities, and then the factors would be the probability piece of the back row, the middle row, and the front row. But this partition function is all the possibilities. Contains all of the possible configurations of the system. Okay. Question? Okay. All right, so and we call that partition function, in this class we call that Q. And so let's do a problem. Let's do a simple problem of just a 3-level system. Does everybody have this? I'll erase it. The partition function is probably the first thing you calculate in any of these situations. And so let's take a 3-level system. Let's use a spectroscopic example, because most of the time those are the examples where we can actually determine how many molecules are in the ground state, how many are in the middle state, how many are in the excited state. I don't know of many experiments other than spectroscopic experiments that can give you that amount of detail as to where the molecules are in the ground state or the excited state. So we have a 3-level system here. I've done the math for 0, 200, and 400 wave numbers. So 0, 200, and 400. Yes. And so this is our energy axis. So it's an energy level diagram. There are 3 energy levels. These are the 3 states when I was talking about Pi. These are the I's. I equals 0, 1, and 2. Wave numbers, are you familiar with wave numbers? It's inverse wavelength, so something's similar to like infrared, we measure the x-axis in wave numbers. It's essentially how many waves you have in a centimeter. Okay, so And so 1 over the wavelength in centimeters is frequency, or is proportional to frequency. And so instead of writing nu by itself, we put the tilde on top. And that indicates that it's wave numbers. Okay. A frequency itself would be c over lambda. And so the distance scale for the wavelength would be canceled by the distance scale in the speed of light. And you'd end up with inverse seconds, which would be hertz, which would be frequency. So frequency is not the same as wave number, but it's proportional to, because it's just 1 over wavelength. You're missing a factor of c. If you wanted to get to frequency from wave numbers, you could just multiply by c, because this is 1 over lambda. Multiply by c, you have c over lambda, and so that would give you the frequency. So you guys just review, a little bit of review perhaps. Notice how I've drawn the energy levels. They're not divided. Like if I had a division there, that would be doubly degenerate, okay? And so these are not degenerate. And so let's calculate Q. Say again?
What temperature?
Let's do this at, I think I did it at room temperature. Yes. And so let's answer this question. What are the different probabilities of being in the ground state, the first or second excited state at room temperature? (298 Kelvin, 25 C). And so let's calculate that normalization constant first, which we call the partition function. I find it's easiest to do this in a table format. Okay. And so let me go ahead and erase this piece down here, and we'll put everything in a table. So let's just label these 0, 1, and 2. So that's our index, I. Okay. 0, 1, and 2. The energy of I equals 0 is 0 wave numbers, 200 wave numbers, and 400 wave numbers. Let's go ahead and write down the degeneracy of all of these, just so we know we've covered that base. So this piece right here, G sub I, or G of I, that is the degeneracy, and it's 1 for all of them. Now we're going to calculate the Boltzmann factor, at least the exponential piece of it. Okay. And so we're taking the energy and we're dividing by KT. Now there's, I guess, a convenient way to do this and a very inconvenient way to do this. If you look up Boltzmann's constant, K here, that's 1.23? 38, and then it's 23 next. Yeah. 38 times 10 to the negative 23 joules per Kelvin. Okay, so that's in joules. And it's also got this really very, very small, 10 to the minus 23 in that. These are very small energies. These are wave numbers, very, very small energies. And so we could do everything in joules, but it's going to be a mess. Okay, and so can we convert Boltzmann's constant to wave numbers? Since our energy scales are in wave numbers, these are nice, clean numbers here. Let's convert our Boltzmann's constant into wave numbers. So how can we do that? We have joules. what can we divide this by and multiply this by to get to wave numbers?
By HC.
Yes. Okay, so what do we, let's look at the units first. So Jerome said to divide by HC. So Planck's constant and speed of light. So Planck's constant is joules times seconds. Let's just do the unit analysis first, okay? Just to make sure this is going to get us someplace. You start putting things in your calculator, I mean, you're wasting time, right? Until you know that's the direction you want to go. And then we have the speed of light. It's in meters per second. And so we'll see that the seconds and the per second cancel, the joules cancel, but we're going to end up with inverse meters, which is not exactly what we want. We want centimeters. So can we write the speed of light in centimeters per second? We can. So let's do the speed of light in centimeters per second, which would be 3 times 10. It would be 10 to the 8 meters per second, and a centimeter's smaller than that. So it ought to go further. It'd be 10 to the 10. 10 to the 10 centimeters per second. And then Planck's constant, 6.626. I'll leave it at 6.6 times 10 to the negative 34 joules per second. So if we take all of this into consideration, it looks like it's going to be pretty nice because we have a minus 34 here plus 10. So that's minus 24, and we have minus 23 on top. And so, again, almost all of those powers of 10 are going to go away. And so K over HC is going to equal 0.695, roughly, wave numbers per Kelvin. So that's nice, right? So now we're down into some units that we don't have to worry about all these powers of 10. Now we've got 3 calculations to do here. We're going to be dividing by KT each time. And so let's just see what KT is at room temperature. And so it's, 298 Kelvin, the Kelvins cancel, we end up with wave numbers, okay? And so it's going to drop that a little bit, it's 0.695, so we end up about 207. So that's our thermal energy at room temperature. That's a great number to remember. And then for my exams, I'll let you bring a note card to the exam. And so it'd be great to have Boltzmann's constant in wave numbers and in joules and any other kind of unit that you might find useful. So Boltzmann's constant here in wave numbers, 0.695 wave numbers per Kelvin. Very useful version of Boltzmann's constant. And then knowing at room temperature, you have about 207 wave numbers. That's the thermal bath that you're in. So any system that it's at equilibrium with room temperature is going to be excited to around 200 wave numbers. So if you have some vibrational modes that are less than 200 wave numbers, they're going to be excited at room temperature. But if you have like a CH stretch, the stretching mode of a CH bond, that's got a frequency of 3,000 wave numbers. So at room temperature, it's not excited. Very important concept to think about. The Boltzmann Factor, or the Boltzmann constant times temperature tells you the thermal energy that you have in the system. So in order to excite a CH stretch to its second or third or fourth level, you would need to have a temperature, when multiplied by Boltzmann's constant, of close to 3,000 wave numbers, which would be quite high. So it'd be roughly 3,000 Kelvin, right? This is 200 Kelvin, and we have about 200 wave numbers of energy. For 3,000 wave numbers, we'd need something over 3,000 Kelvin. Molecules are not going to survive that. And so you're never really going to have thermal excitation of a CH stretch. but a big old bending mode, it's like 57 wave numbers, like naphthalene bending like a plank. You know, that's going to be excited at room temperature because it's moving a lot of mass and has a really low frequency. So that's just a little side note on thermal energy. At room temperature, you have about 200 wave numbers of thermal energy available. And our first excited state is 200 wave numbers. So we're certainly going to have some excitation into this level and some excitation into this one. Okay. So now let's take those energies and divide them by the thermal energy that we have, and then take the exponential. Okay. So this would be e to the minus 0 over kt, which is equal to 1 because it's e to the 0. And this piece is e to the minus, and I'm going to go ahead and make this one 200 instead of 207. Okay, this is e to the minus 200 wave numbers over kt, but kt at room temperature is 200 wave numbers. So that's e to the minus 1. So I've done on my calculator. It's 0.37. Okay. And then the next one is e to the minus 400 over 200. Are we going to run out of time? What is?
6 minutes left, I guess.
Okay. And then that one's going to be 0.14. Notice how the Boltzmann factors start at 1 for the ground state, because that's e to the 0. And then they get smaller as you go higher in energy. They kind of look like probabilities, don't they? But they don't sum to 1. They're not normalized. So that's why we take this sum of all these Boltzmann factors and create a normalization constant. And then we divide each one of these by that normalization constant to get a normalized set of probabilities. So down here, this Q is equal to the sum of all 3 of these. So we sum all 3 of these Boltzmann factors. We've got to make sure we take into account the degeneracy, but it's 1 in all 3 cases. And so we have 1 plus 0.37 plus 0.14. 1.50. And so now we can calculate the probabilities, our populations of these 3 different levels at room temperature. So this is 1 over 1.51, 0.37 over 1.51, and 0.14 over 1.51. So we end up with 0.66, 0.25, and 0.09. And you can check your work, they should add up to 100. Okay, that's 11 and 9, 20, so 2, 8, 9, 10. So this is a nice thing if you end up at the end and your probabilities don't sum to 1. Something's gone wrong. And probably you forgot to take into account the degeneracies. Okay? So this is a nice thing. You can check your work. Oh, that's always enjoyable. And now let's analyze this. This says there's a 66% chance to being in the ground state, a 25% chance there, and a 9% chance there. So even though at room temperature I have only 200 wave numbers of thermal energy, I can still have molecules that are excited to 400 wave numbers. Now one other thing that we can add to this is what is the average energy? So the average energy is going to be this piece. Let's do this in a different color. So it's the energy times the probability. And then the contribution of this level is 25% of the molecules have 200 wave numbers. And then 9% of the molecules have 400 wave numbers.
This is also called the internal energy.
This is the internal energy. So this is the internal energy of the system. And we call that U. So that tiny little equation down at the bottom, the internal energy is the sum of all the individual energies times the probabilities. And so in our situation, we have 86 wave numbers. That's the internal energy of our system. Notice how if you did an experiment on this system and you pulled molecules out, you would never observe that energy. Ever. Why? Because if you do a test on the system, there's only 3 answers of energy you're going to get. You're going to get 0 wave numbers, 200 wave numbers, or 400 wave numbers. Okay? So this internal energy is an average. It's a statistical average. That's the average energy of the whole system. Even though individually, you only have 3 options, 400, 200, or 0. And so these thermodynamic averages are probabilistic. Over time, like if you pull out, you're going to pull 66% of the time, your answer is going to be 0. And 25% of the time, your answer will be 200. And 9% of the time, your answer will be 400. Average all of those together, and you'll get 86 wave numbers. And that's at room temperature for this particular system. Now, next time, what we'll do is we will put degeneracy on these upper 2 levels. And so we'll have a 2-level degeneracy here and 2 degeneracy there. Same temperature, same energy differences, and we'll see what happens to the average energy. And you'll learn that even though the temperature is the same, the average energy has gone up. Okay, and so we'll do that next time. Okay. Again, thanks for your work on the problems. Keep that up, and also the Quizlets. Again, the vocabulary is not the main point of the course, but once we learn those terms, then you'll understand more what we're talking about in lecture. You'll be able to use them in your problems. So that's the foundational level of knowledge. So keep up the good work.